Okay. Now we can do woohoo for Friday. Okay. All right. Woohoo. Okay. Good. So. Woo. Okay. 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 We'll get started now. Okay. So, lecture in a minute. I'm going to tell you what I'm going to tell you in a minute. Okay. So we did explore last time. We talked about this procedure explore, which is a recursive procedure that explores a graph in some way. Now it's recursive, meaning recursive means that we use a stack, right? Because there's a recursion stack that's being used. So there's really a data structure there underneath this graph traversal, which is a stack. And you're going to learn to love the stack today. Okay, we're going to talk about how things come on and off the stack in great detail because we'll use those properties to develop some algorithms. Okay, so and the notion of that notion of time on the stack are these pre and post orderings. It gives you, for example, we'll give you a quick gift with a cycle test using this pre and post order numbers, and then we'll look at directed graphs and see how all this works on directed graphs, and finally, we'll show you how to do this thing called a topological sort, meaning that if your directed graph doesn't have a cycle, you can sort it so that every edge goes from lower number to higher number, okay? Or lower position to higher position. All the edges go in order. And there's two algorithms. One is going to be based on this post order thing, which is basically the time you're popped off the stack. And another algorithm is peeling off the sources. And we'll discuss that. A source for a directed graph is a vertex that has no end degree. Okay? So that was the lecture, so you understand completely, right? Okay, so hopefully by the end you will. Okay? So explore. We're going to review this explore procedure we did from last time. Okay? Now just review a little bit for graphs. What is the size of the adjacency list representation for a graph? Okay, I have a graph, D equals VE. What's the size? Okay, you want to answer? Is that why you have your answer? Okay, so what's the answer? 2E. Okay, that's right. Okay, this is good. He's very excited because that's my favorite theorem. And so maybe, perhaps it's his favorite theorem as well. So but I do order O of E plus E, but he's doing it better. He's saying it's exactly 2 times the number of edges, right? That's the number of things in the adjacency list. Okay, I guess I'm adding size for the empty spots. Okay, so explore was this graph, this procedure. You would when you explore a vertex V, you first mark it with chalk, right? You set the visited value to true, and then you explore each room you can go from there. Or so you go over each edge and you look at the other end. If that vertex is not explored, then you call the procedure recursively. Okay? And where's the stack? It's in the recursion. Right? I don't explicitly maintain a stack. One can write code to do all this with a stack explicitly, but we're just using recursion. Okay? So the property is all and only nodes are reachable from A are reached by explore. So if you start at a vertex A, if you call explore on some vertex named A, every node that's reachable from A by a path, if there's a path from A to any vertex, explore will actually explore it. Okay? So reachable means there's a path, and the argument for this property is if there is no first unexplored node on this path. That's the argument. Okay? Well, clearly the first node is explored, and then since at some point, if there was a first unexplored node, the previous node would have been explored, which means explore would have been called on this node. Okay, that was the argument. Okay, so and then the runtime was order V plus E. Why is it order size of V plus the size of E? Why is that the runtime? How did I argue that was a running time? Right? Each node is explored once at most, right? That's one of the things. And in the Explorer thing, what we do is we go over the adjacency list. And how big are the adjacency list? 2 times Z. Okay? So that's the total time is order V to explore each node plus Z. Okay? I mean, this is an upper bound. Maybe if it's disconnected, you can do, or you don't see all of it, it could be less. But this is an upper bound. Is that clear? Okay. Okay. So the time is, the argument here is the time is proportional to the total size of the adjacency list. Always, always, always in this course is you have a property, but you can try to remember the property, but personally I always like to try to understand why it's true. Okay? The ideas and the concepts here are easy enough where you should be able to, and that's how we examine you. Okay? If, by the way, we expect you to be able to argue such things are true. Okay? I mean, you've already experienced this in 70, right? So this is not new to you. Okay, so depth first search is nothing more than just doing this many times. So depth first search, the procedure is for each node U. First this is the outer loop in some sense. You just set you set up the visited vector to be all false for everybody. You clean off all the chalk, right? And then for each node U, if it's not visited already, you explore it. Okay, so this is like the inner. It's like you just go over all the nodes and explore it. So this will explore the whole graph, and that running time is order V plus Z as well, because in some sense that was the upper bound we were using. Okay, so intuitively, what does it do? Like if the whole graph is connected. Right? If there's a path from the first vertex to everything else from the first vertex you explore, then you've already explored the whole graph. And every other time through this loop, it'll do nothing, right? Because they'll be visited. Does that make sense? This visited vector is being used inside of the explorer procedure, and it will mark it. Okay? So intuitively, we saw this before with this explorer. You get this tree out, this tree that corresponds to sort of essentially the execution traces, the tree of recursive calls. Okay? And you get a tree for each connected component. Okay, and several trees are a forest, right? That's what, if you have more than one tree, you're in a forest. That's what we call them. Okay, so now how do you output the connected components of a tree? Of a graph. Now I give a graph, and you want to just say, oh, these vertices, this vertex is in connected component 1, and this vertex is in connected component 2. Now clearly, depth first search can be used for that. So we're going to show you how to do that. Okay. So what we're going to do is we're going to beef up Explore, and we're going to say because and what we're going to say is visit it. We're going to add this procedure pre-visit. Okay, once we set visited to true, we do some pre-visit. And then after we look at we explore all the neighboring rooms, including maybe making recursive calls. And once we come back, and right before we exit this procedure, we do a post-visit. We call this post-visit procedure. Okay, so the pre-visit procedure, this time we're not going to use the post-visit procedure. It's going to be nothing. It's going to be defined as pass, I guess, in Python. And a pre-visit will be set the CC number. So what we're going to do, the output of this algorithm is going to try to label every vertex with the component number. Okay? So if you want to see if two guys are in the same component, you see if they have the same number. Right? Okay? So we're setting this CC num to this, and now for depth first search, what we do is for each vertex in V, if it's not visited, we explore V. That's what we saw before. Plus, we add this procedure. Every time we do one of these explores, we add 1 to the CC number. So initially, it's 0, right? CC number is 0, and it's okay. And so the first explore call will label all the vertices that are reachable from V with 0, and then the next time, CC number will be 1, and the next time you call explore on a vertex, it will label everybody 1, and so on. Okay? So each node will be labeled with a number, and any two nodes with the same number will be in the same connected component. Okay? Okay. It's just the output format. It's just the way we're doing it. Okay? Okay, so now, okay, let's just watch it, I guess. Okay, so we'll start somewhere, right? So you see what happens here, right? So you start here with the Explorer. You go here, right? Okay, what's on the stack at this point? What's on the stack? Yeah, the Explorer call for A, you can think of it as, again, my thing is a little bit odd. A is on the bottom of the stack. F is on the next to the stack. F, and then what will be on the stack next? C, right? Now it's on the stack. And now D is on this Explorer of D is on the stack. Okay? Now, when D looks at this neighboring edge, what does it see? It says, well, it looks at this neighboring edge. It's an edge. It sees that C is marked, right? It sees that C is visited, so it doesn't explore C. Otherwise, you'd have an infinite loop. And it looks at this edge, and it looks at F, and it says, oh, you're marked as well, so I'm going to not explore you either. Okay? But this edge is kind of funny. What is it called? What do you know here? It's not one of the tree edges. What is it? It's sort of never going to be red in some sense, right? So what does it create in this graph? Yeah, it's a cycle. Okay, so this is an interesting sort of edge that happens here in this execution. So D has nothing to do. You can't call Explorer on anything. C is already called Explorer on all its neighbors on D. F has already called Explorer on C. Now F calls Explorer on G, and so on. Oh, I pressed the wrong button. Okay, and then so now what happens after you get it out? Every time our pre-visit marked each node with a 0, right? Because that's what it said to do. It would call pre-visit, and it would set the CC number to 0, and that's what these numbers are. Okay, and now the CC number is 1, and you do this. You label B1. B calls Explorer on its neighbor E, and there you are. And you come back, and now the stack is all clear, and DFS is done. Okay, now it may loop over and say, but I need to check E. But what it does for E inside of DFS, it'll look at E, and it says it's visited. So it won't call Explorer on it. Okay? So it's sort of depth first search and painful detail. Okay? So now when we're going to navel gaze a little bit on this algorithm, right? We're going to really look at what's happening. Okay? And I sort of already set it up by sort of obsessing about the stack. And so we're going to do that here a little more. Okay, so what we're going to do is we're going to say, well, how long is everything on the stack? So we're going to set up these two procedures, pre, which will set this pre-label for this vertex to the clock. And then it increments the clock by 1. Okay? And then post sets this post label to the clock value and then increments the clock by 1. So it's just keeping track of all the calls and the returns from the Explorer and saying when does something happen. Okay? So the pre and the post, you set the clock to 0. Now, how far does the clock go up to? If, say, you have a connected graph. If you do an Explorer on a connected graph. Or even not, yeah. What does Explorer do? Do we call Explorer on every node? Okay. And so how high will the clock go? Well, we increment the clock when we first call Explorer. That's when we first call, right? Pre is called here in Explorer, right? Pre-visit and post-visit. So it's called, pre-visit is called once for each Explorer, and post-visit is called once for each Explorer. And how many Explorers are there? There's V. So the clock goes up to 2 times the number of tree edges. Okay? Every time you go across the edge, you get another clock. Okay. So now we can say, let's look at this pre-post interval. That tells you how long you're on the stack. Yes? It's just 2 times the number of nodes. I should have said 2 times the number of vertices. Because we increment it every time. Yeah, 2 times the number of vertices. So if it's connected, it's the number of... Yeah. And each time we call explore, we call pre and we call post. And each one increments the clock. So we're sort of counting the time as when we when we enter a procedure and when we leave. So it's 2 times. Okay. That should be, I'll fix that. It should be 2 times the number of vertices. Okay? But, okay, so anyway, that's mostly for intuition. This is what you really want to know. Here's this property. Now, we have 2 nodes U and V, and there's pre of U and pre of V, of U, post of U are just an interval, 2 numbers, right? The first one's lower than the second one because you're pushed on the stack before you popped off it, right? And so, this is true for U and V as well. And now I want to claim that if I look at all of these are intervals. They're either completely disjoint, either that's 1, 2, and this is 5, 6, or that's 1, 8, and that's 10, 12, or one is contained in another. Okay? And that's because of the stack, right? Right? What happens is if they're ever on the stack at the same time, when did this one go on? Onto the stack? Did it go on before or after you? Before, right? When you have a stack, and it looks like this, this was put on after V, right? So this went on before, okay? And when is it popped off? U. Eventually, it's going to be popped off. And when is it got to be popped off? Is it going to be popped off before or after U? After. Okay? So if 2 nodes are on the same stack, so this interval is the time you're on the stack, right? It's when you're first put on the stack and when you're finally taken off the stack. That's what this interval is, right? The pre is when you're put on the stack, and the post is when you're taken off the stack. So in this picture, you can see that this guy's interval is put on. This node is put on after this one, so its pre is after this guy's pre. Moreover, this guy's post, this guy has to be taken off before this guy's post, this guy. So U's post will be before V's post, which means that this guy's interval will be contained in this guy's interval. Okay? It just says he's on this. If they're on the stack at the same time, one person, yeah. So either both are on the stack at some point, or they never were on the stack at the same time. Now, if they were never on the stack at the same time, that means this guy's whole interval, this guy, the other guy was not on the stack with them. So it means that one node was put on the stack after the other node was popped. So they must be disjoint. Its pre is after the first guy's post. Okay? So that says, this is just some properties. These pre-post intervals, which we're going to play around with quite a bit, they have some properties, right? Either everybody's contained, either one is contained in the other, or they're completely disjoint. And that just really comes from thinking about the stack. Okay? Okay, so, we can just do it. Here's a way to, I don't know, running examples is always, I don't know. So you put it on, you label its pre as 0, you label its pre as 1, you label its pre as 2, and again, these things are going on the stack. They're all on the stack at the same time, all the blue ones. Then what do you do for D? You're going to pop D off the stack. And then you're going to label with its post order number, which is 4. And their post order number is 5. Then Now, look, what didn't happen here is F didn't get popped off the stack, right? So we're not labeling it with this post number. Okay? We keep exploring from F. We loop to the next edge, right? And we look at the next edge, which is goes to G. You explore that, and then you pop right off. That's 7, 8, 9, 10, 11 for the pre. Post is 12, and post is 13. Okay? So this is and it's all, you can see it. You can think about the stack while it's going on. Okay? Now, if you explored an edge UV, let's say if you explored an edge UV first from U, then if now these are always difficult to parse. What is this saying? This is saying this guy's interval is in this guy's interval. Okay? So who was put on the stack first? Who was put on the stack? It's written. Okay, so, right? Okay, who was put on the stack first? Now, you should parse it and verify this to yourself. Right? Why is U on the stack before? Because this interval is in this interval. That means this pre is before this pre. Right? So that says U was put on the stack before V. Moreover, if U was put on the stack before V, it must better be popped off the stack after V. Okay? Okay, and that would be a tree edge. That would be one of these edges where if you explored UV first from U, if that's the first time you saw this edge, you saw it from U, this would be a tree edge. It would be one of the red edges if the interval is contained in the edge. Okay, this will be more powerful when we get to directed graphs, but I just want to warm you up. Okay, so back edge, and now there's this one edge that looks like this. That blue edge from D to B is explored first from D. Okay? And at that point, you have V is on the stack first. Right? So that would say B is on the stack first. So this is what we call a back edge. Okay? And what it tells you is that, well, it tells you that either the edge is a tree edge, or every edge goes back to a previous node that's on the stack while you're running. Right? There's no edge from D to E. Right? So these are the only two possibilities. One interval is contained in the other, or either one of the two intervals is contained in the other for each edge. Okay? They're not disjoint. The intervals are not disjoint for these guys. Okay? Like the interval for, let's look at a disjoint example. For F, 10, 13 is disjoint from D's interval, which is 3 to 4. But D's interval, 3 to 4, is contained in B's interval, 1 to 8. So this edge from D to B is called a back edge. Yeah. No, the back edges they're not opposites, right? I mean, in some sense, it's just what I'm saying is there's a tree edge, which is what you're exploring on, and what you're building a tree. You're going to get n-1 of those, and then you're going to have a bunch of these other edges. Yeah, these are tree edges. Yeah, no, that's what I'm saying. It's the edge. You have to see that it was explored first from U to V. Like, what could have happened is they could have built a very different tree. Okay? What he's saying is that it really depends on which order you do these things. What I could have done from B is that I have to explore. I'm just assuming my adjacency list. B is adjacent to C and D, and G, right? So I assume that they're in alphabetical order. So the first edge that B explored was C. But if I had made the adjacency list in a different order, if I could put D first, then B would have explored D first, and then this would have been a tree edge, and this would have been a tree edge, and this would have been the back edge, right? So depending on the order of the adjacency list, I could have many different trees that are output. Yeah. Okay? Okay, so there's no edge between U and V if there's disjoint intervals. So these are all the edges sort of have this property. One endpoint is contained in the other, and if you see who explored what first, you could tell whether it's a tree edge or a back edge. Okay, slightly. It's a little easier, actually, in depth first search to understand this, but I mean in directed graphs. So we'll go to directed graphs. Okay. So we have vertices V and edges which are a subset of V cross V of the pairs of vertices. Okay. And an edge UV, now it has meaning. It has direction. It means it goes from U to V. So the tail is U, the head is V. Here's some examples. Here's a graph. It's the same graph as before, except I've added a few arcs and I've directed them. So the vertices are A, B, C, D, E, F, G, and this edge is A, B, and it goes from A to B. Okay? And this is called the head, and this is called the tail. Okay? Just some terminology. So this is a directed graph. Okay? So the root is the starting point. I'm just going to define some things. Even now I had some terminology here. Now I'm going to have a terminology with respect to the algorithm, which is you have the root, which is the starting point of the explorer. We can run explore on this one as well, right? Okay, can you write an adjacency list here? Let's actually think about. It's all about explorer is just something that works with adjacency list, right? So what's the adjacency list for A? B, E, F, right? What's the adjacency list for E? It's not A. Okay? It's only where you can go to. Okay? Does that make sense? That's the difference between undirected and directed. Is a set of adjacency. If you think about them as a representation by adjacency list, it's a E can go to V, F, but it can't go to A. Okay? Okay, so root's the starting point. V is an ancestor of U. If V is on the path from or to the root. That's what we're going to say. Okay? Because I need to define ancestors. Okay? V is a descendant of U. When is V a descendant of U? Yeah. When U is an ancestor of V, right? It's right. Okay. Okay. So let's just do it. I guess we can do an example here. We see A goes here, and we've seen this example a couple of times. This time, it didn't go to C, right? Because it can't. That edge is in the wrong direction. So B's adjacency list only has D and G in it. So it's going to explore D first, then it explores C, and then C says, should I explore B? I should not, because that node is visited. So I won't explore it. Okay? And so then it backs up, and we're doing the whole post order thing again. There's 6, 7, 8. That's how long B was on the stack for 8 time steps in this algorithm. A still has outgoing edges it can explore. It goes here, and then F tries to explore this one, but it can't. Okay, and then it comes back because that's already visited. Why doesn't it go to D? Why doesn't it go to D? Yeah, it's marked. Right. Okay, excellent. Okay, so good. Okay, so that's so in some sense here we could also look at the pre and post order numbers. The tree, there's two kinds of edges here. The tree, which are the red edges, and then there's this sort of purple edge here that goes forward. And you can see why it's called forward, right? It goes to its descendant, right? From A, it goes to F, which is a descendant of A in the tree. Okay? It's forward. The tree edges also go to descendants, but it goes to direct children, right? And now the property for the pre and the post is, now if I take the pre-post interval of V, if it's in the interval for U, that tells you that V is a descendant of U. U must be on the stack when V is explored. That means U's interval contains V's interval. Okay? Okay, so here's an example of a forward edge. AF is a forward edge. So let's look at the interval for F, which is 10, 11, and we see that it's in 0 to 13, right? A was on the stack when F was on the stack. Okay, for the whole time f was on the stack. Okay, and this is what I mean in, right? It means that this guy's pre is before this guy's pre, and this guy's post is before this guy's post. Okay? And now there's also these back edges. Do you see a back edge? Where do you see a back? That goes to your ancestor. Okay? So here the U and V's are, here it says the heads interval contains the tails interval. Okay? Okay, if the heads interval contains the tails interval, it means the head was on the stack the whole time when the tail was on there. Right? So it says this edge goes to an ancestor. V was on the stack longer, so it must be higher up in the tree. Okay, so it's a back edge. Okay, and that's what, here's an example. Here's an example, CB. Right? CB was on the stack for time period 3 to 4. It's in the time period 1 to 8. Okay? There's also this weird cross edge. Here, there's edges. Here, what you've done is you've explored this whole subtree over here. In this first, when A goes and explores B, it explores all these nodes over here. Okay, so if this was undirected, that guy would then cross this edge, right? Would explore F. So these cross edges did not exist in the other, for undirected graphs. There are no cross edges. We have cross edges because you can't go from D to F, but once you go to F, you see D is on your adjacency list, so you go look at D, and then you don't explore it. Okay, so those are disjoint intervals. So for undirected graphs, you can have vertices with disjoint intervals that are connected by an edge, as long as they're directed in the right way. Right? So, and the right way is this guy's interval, 2, 5, is entirely before this guy's interval, 10, 11. Okay? You can't have an edge from here to here and this guy's interval be after this guy's interval. Because when you explore this guy, you would then also explore this guy. Okay? Okay. So 2, 5 is entirely before 10, 11. Okay. So there you go. Wish there was a clock in the room. Okay. Okay, so let's just see. So the tree edge is a direct call of the tree of the explorer. The forward edge is an edge to the descendant. A back edge is an edge to the ancestor. And a cross edge is everything else. Okay? Okay? So now, let's say I have a directed graph without cycles. And here's what a cycle is. A cycle is a sequence of vertices where there's an edge from V0 to V1, an edge from V1 to V2, all the way to VK, and then from VK back to V0. That's what a cycle is, right? It's a sequence of edges that come back to the beginning. Okay? Okay, why do we care about directed graphs without cycles? Well, because, there's social norms, right? If you say hello and you say goodbye, you should always say hello before you say goodbye. Otherwise, you're not following the social norm, right? And it's very important to follow the social norm, right? So you need to code up all the interactions you have with people as an acyclic directed graph, okay? So, and this is a fairly simple one, okay? Remember, hello before goodbye, okay? There's other things you can do. This is the dependency graph for some compiler or some package. And what do you want to do with each one of these modules? You prefer to sort of, if there's a cycle in these modules, is that a problem? If they all depend on each other, right? That's a problem. And it's also a problem in social orders. If you have social roles that define precedence and there's a cycle, there's a problem there, right? Okay? It's the chicken or the egg sort of thing. Okay? So, and you obviously, so you want to figure out whether, let's see how to even figure out whether a directed acyclic graph has a cycle or not. Okay? Okay, does that have a cycle? It has a cycle? Okay, yeah, it has a cycle. Okay, so, I mean, it would have been a little harder to tell if I drew a few more arcs, right? I mean, it's not that easy of a thing, right? I mean, you can just, it pops out at you, but when you're actually trying to even tell whether a graph is acyclic is like not that easy, right? You have to figure out whether there's no cycles. Especially for undirected graphs, you can almost count the edges. It seems much simpler. For directed graphs, you could have a lot of arcs in the directed graphs, and it could have no cycle, right? You could have n squared arcs, okay, or edges. Okay, so now let's look at this. Look at this back edge from u to v. So that's the interval v contains the interval u. That's what the back edge here is. The interval for this vertex b, 1, 8, contains the interval for c, 3, 4, right? Okay, so that's what a back edge means. And now if I see a back edge, do I know I have a cycle? Why? Yes.
Because if you would go from B to C somehow, and you could then go from C to B, then you could go from C all the way back to C again.
Right. Okay, but the somehow you fuzzed a little bit, right? You fudged a little bit on somehow. What do you mean somehow?
You can take, if you have a known route from B to C.
Yeah. If you have a known route. Why do I know I have a known route? C is a descendant of B. Right. That's right. Okay, because, well, why do we know it's a descendant of B? Because B is on the stack when we're exploring C. Okay? Meaning, how did C get on the stack? Well, B put it there. Right? B explored something, which explored something, which explored something, which eventually explored C. Okay? So if C is on the stack, when B is on the stack, and B is on the stack first, there's a path from B to C, right? If U and V are on the stack, and V is on the stack second, there must be a path from U to V, right? Because all those are explore calls. Each explore call corresponds to a directed edge in the right direction. Okay, that's the somehow, and that's what he said. Okay, so there's this back edge, which is an edge to an ancestor. They must be an ancestor in this tree, right? Because the explore calls are the ancestors. Okay? So the tree edges from V to U. Okay? So if you have a back edge, then you're going to have a sequence of tree edges from V to U. Okay? Because this is an edge to an ancestor, which means that V was on the stack before U. And then that means V had a sequence of explore calls, which means there's a path from V to U. And now you have an edge from U to V, so you have a cycle. You have a path from U to V to U, and then an edge from U to V, so you have a cycle that starts at V and returns to V. Or the way he said it, it starts at U and returns to U. Okay? So a back edge means a cycle. So there's one way to detect a cycle. If I just, all I need to do now is do this very trivial thing. Well, I just check for each edge and see if they're back edge. Right? That's all I have to do. And then I know there's a cycle. Right? But will I always find all the cycles this way? Right? So is there a way to have a cycle and not have a back edge? Right? So that's the question. So a back edge, already we say, okay, we can run this algorithm. We have this weird pre and post. And now you got a payoff. You just, for checking a back edge, it's trivial. You just check the interval of U versus the interval of V. Right? So it's a trivial algorithm. If you find a back edge, you check for all edges. You know there's a cycle in the graph. Okay? So now you've got a little power. Okay? But is it true that if there's a cycle, you always have a back edge? Maybe you miss it, right? Okay. So now I'm going to argue yes, right? As somebody helpfully pointed out, is that if there's a back edge, that if there's a cycle, there's always a back edge, right? Now the reason I'm asking you to, okay, so here let me just show you. Okay, so the back edge means there's a cycle. That's what we argued on the previous slide. If there is a cycle, I want to argue that any depth first search, right? There's all kinds of different depth first search depending on the orderings of the adjacency list, right? But however it's ordered, I want to say it will discover a back edge, right? So what's a cycle look like? This is what a cycle looks like. Okay. Now, at some point, you're going to explore V, the some node on this cycle, right? Because you're going to explore every node in breadth depth first search. That's what it does. Okay? So let's assume V0 is the first one explored. Okay? Now, all the nodes on the cycle are explored when explore V0 returns. You're sure of that, right? Because if they're not explored, V0 has a path to it. We know that explores everything reachable from V0 before returning from V0, right? And so therefore, it explores all of these nodes, okay? So that means that all of their intervals are inside of V0's interval. Okay, V1's interval is inside of V0's interval because V0 was on the stack first, and it's going to be popped last. Okay? And so on. So V1's interval all the way up to VK. So VK's interval is inside of V0's interval. So therefore, what is the edge, VK to V0? Right, it's a back edge because this guy's interval is inside this guy's interval. So that's a back edge. It's an edge to an ancestor. Okay? So now I've argued that the cycle implies there's a back edge. So this is a quick algorithm to tell whether there's a cycle in your graph. Okay? It's very nice. Okay. So that's all great. It's like now I know the graph doesn't have a cycle. What did I really want to do? Okay. So this is order V plus E time for each edge. All you have to do is check whether the intervals are contained in the right way for the back edge. Okay, so this is a fast algorithm for saying something's acyclic. Okay, but what we really want to do is these guys have no cycles, and we can tell in linear time, right? So that's nice. Okay, well, what good is that? It's not much good, right? We really wanted to do something else, right? We really wanted to find an order that's consistent with these arrows, right? Where all the arrows go from left to right, for example. Okay? So this is you want to find an ordering where each edge goes from an earlier vertex to later in an acyclic graph. So I want to order the vertices so they're in that order. Like this is an ordering, right? You want to say hello, and you can have dinner. You better not have dinner without saying hello. These are sort of a precedence graph. So this is one ordering. And you notice all the arcs, their tail is to the left of their head. Okay? I mean, this one has two topological sorts. You could have tea before or after dinner, I guess. I don't know. I don't really drink tea. Okay. Well, I drink it sometimes. But you could have it both ways. I don't know. Okay. So now we can. So now this graph, I've removed an edge, and I'm going to try to find a linear ordering. Okay. This one's a little bit harder, right, to figure out who goes first and everything. Right. Okay. So let's. Is this? Oh no. It may not be different, but we'll see. Okay, so it's not different. Okay, so this is a linear ordering. Now, so the one thing, it does linearize it. You can check A, E. What you have to do in some sense is check every arc. Okay, but let's check a random arc. Let's check F goes to D, so F better be before D. A goes to F, so A goes to F here. Okay? Okay, so when is A? Now, A is first in this order. Okay? And in this DFS, when is A popped off the stack? What? Last. It's the last one popped off the stack. Okay? When is E popped off the stack? 12, at number 12, right? It's the second to last one that's popped off the stack. Okay? and so on, right? BF is the third to last one that's popped off the stack. Okay, so what this ordering is, what I've written down as an ordering, is just inverse of their post-order number. Okay? This guy has the highest post-order number, so I put him first. This one has the second highest post-order number, so I put him second. This one has the third highest post-order number. B has 8, it's the fourth highest post-order number, and so on. Right? And that's the ordering here. Now, I claim this ordering, every edge in a DAG, UV, has a post-order. If you have a DAG, you know that the post-order of U, for any arc from U to V, the post-order number of U has to be greater than the post-order number of V. Right? And this is, again, from the property of the stack. It's a little hard to catch, but, right? There's no back edges, and that's because there's no back edges. Okay? It says that in a tree and forward edges, the interval of U contains the interval of V, so that tells you get pre of U, pre of V, post of V, and post of U, right? So you don't have, for this arc, you have that post of U is after post of V, which is what the argument says, right? Post of U is after post of V for this arc from U to V. The cross edge, the whole interval for U is greater than the interval for V, which tells you that post of U is definitely greater than post of V. And there's no back edges, okay? So we know that for a DAG, for every arc, post of U is greater than post of V, if the arc goes from U to V, okay? So where should you put U relative to V? Before it, right? So you should output, if you output a reverse post-order number, now you know for every arc, it'll go from, it always goes from a higher post-order number to a lower post-order number. So every arc will go in the right direction, from the earlier vertex that you output to the later one. Okay? Okay, so this is why, now it becomes really easy to say, oh yeah, that's true, right? There's no back edges, so we have this condition. So if we just sort by the inverse post-order number, then we're done. Okay? Okay, so that's pretty easy. So there's one other way to get, just before we go, I just want to give you a quick another way to find the here's you saw before, a source is a node with no incoming arcs. So let's look at an example. Where's the source here? A is the only source. Okay? What if I removed A? If A is a source, do I know I could put it first in the topological sort? Right? There's nobody who's going to have an arc that comes back to him. Right? He has no edges. So there's a source. If I remove them, if I remove A, is there another source? Yeah, E is a source then, or B is a source. And then I could put them next, right? Because all their incoming arcs come from nodes before them. Okay, so this is another algorithm to find the highest post-order number is a source, the lowest post-order number is a sink, right? You can actually start playing with this. Every DAG has at least one source or one sink, right? If you have a topological sort, the first node can't have any incoming arcs, right? Okay, so here's another algorithm. You could find a source, you could output it, and repeat. Okay, so naively, this takes order NM, but if you think about it for a little bit, you can make it very efficient and make it order M. Okay? And this is it's going to be useful it's going to be useful later. Okay? It'll be useful on Monday. Okay? So, but I just want to see these two algorithms. Let me go back to the lecture in a minute here. Just a second. Okay, yeah, so I'll let you go, but you should understand all this. And happy Friday.
Why can't I grab a node be connected to itself?
What?
So in a graph, why can't a node have an edge to itself?
It can.
It can?
Yeah. If you want. I mean,
It'll still be a valid graph.
yeah.
So how?
I mean, sometimes they define graphs to be simple, where they don't have self loops.
Okay.
But you can, if you want to have a graph can represent anything you want,
I see.
right? And so there's like a Markov chain.
I see.
It has arcs to itself, right? They
But
represent.
I feel like that situation would be super hard because like in a stack, how would you do that? You would let's say A is there, A has its own loop.
Yeah, you marked A,
So you mark A,
and A is
you
J.
go back to A.
It looks at A and sees that it's marked,
So it has
and
the
then it
same-
doesn't go there.
But would it have the same post order and pre-order? Or
It doesn't. It doesn't explore it. It only explores it once,
Oh, I see.
right?
Oh, it doesn't explore it. That makes sense.
Because it looks at when you first explore A, you mark it.
I see.
So, and now you go through this adjacency list and say A is on its adjacency list.
I see.
It will look and see if that A is marked.
Okay, now here's my follow-up question.
Uh-huh.
What if A has some other node it's connected to,
Uh-huh.
and it's unexplored, and now because of this, since you visited it, you popped A, but then you have some other node that is also connected.
Well, you would. It would be on your adjacency list. So A would maybe look at A and see that it's visited and not look at it, and then it would go to the next element of its adjacency list, which is this other node,
Okay.
and then it would explore it.
So we wouldn't pop in that situation.
You when do you pop? When you exhaust your adjacency list.
Oh yeah, right. It's not when you see. Okay.
Yeah, you don't pop as soon as you see
So those
side
are
neighbor.
two different ideas.
Yeah, there's